Okay, so the rest of the afternoon, we have one lecture, one workshop, and it's on troubleshooting. And looks like Cam taught this one last. Kind of sarcastically, it ran, so I'm done. So just because it runs does not mean your model is good, and you're done with it. So that's the kind of strategies we're going to be taking on in the next bit here. We're going to talk about these categories. Built-in data checking, something that really makes RAS way, way more usable is these couple things here. Don't let you put in wrong data. Like if it's expecting numbers, you can't type in letters. When it runs, it generates errors, warnings, and notes. But before it even runs, it looks to tell you whether or not you have a complete model. Rather than if you haven't put in a parameter, it doesn't assume 0. It says you have to go put that parameter in. And that has saved much heartache over the years. The steady flow engine will generate these errors, warnings, and notes. We'll look at some of those. There's something called log output, which is more like you're interested in seeing how it actually works behind the scenes. That's not for regular debugging, but we'll still see how you can get out of that. And then we'll talk about a little procedure for how to go about doing this on a day-to-day basis with the RAS results. Okay, so the built-in data checking, some things got range checks, like if it's an n-value, you can't put in 0 or a negative number, just won't let you do it. Alphanumeric checks, like I mentioned, that if it's expecting a number, you can't type in letters. In some places you can copy and paste them in, but don't try to defeat the system. We're trying to protect you there. Some things have to be monotonic. Like you're putting in a profile, the stationing has to be greater than or equal to the one before. Some places we check that while you're doing it. Other places we check that just before compute. Data consistency. So there's many levels of that. One of which is, on a big level, is if you're going to do a run in RAS, you need to have those 3 files. You need to have a geometry file, a flow file, and a plan file. And there's only one kind of geometry, but there's several kinds of flows. It could be steady or unsteady. So your plan and your boundary conditions and stuff, those all have to work together. And that's the consistency on a big scale, and then consistency on a smaller scale. Like if somewhere in the middle you refer to something like, I'm going to go get something out of DSS to get a time series, well, that file needs to exist. Data deletion warnings, a lot of levels on that. If you delete something small, I'll let you do it. If you delete something big, then you get a really? Really, really? Okay. Things like that. Here's the monotonic. So you're on a cross section, you try to you're putting in a profile, and it wasn't increasing. So you're looking at that table, every station value needs to be higher than the one before, greater than or equal to higher than the one before. And so that'll give you a warning like right then, because we don't let, if I can find there's going to be a problem, there's no way this is going to ever work, and I can tell you right now, then don't let you get too far. And it's just telling you, hey, okay, you don't have to fix it right then, but you'll need to fix it at some point. But it's nice to know right when we know you have the problem. So that's that level. Now this other one, this is what always happens before any run, and it goes through the whole data set and looks at every parameter that is going to be needed for that run. So at that point, when you're going to make a run, we know what you're going to do. Are you going to be doing a steady flow run, in which case you need to have all these parameters, and if you do unsteady, then it's those parameters plus a few others. But if you're missing things like you don't have any n values set, then this is the kind of messages you get. We've had requests over the years that, hey, if you have an error list, can I double click on it, it'll take me to that problem? That's a really good idea, and we'd like to do that, but we didn't set it up just to do that. Maybe in a future version. When the steady flow engine runs, it writes a binary output file, and it has the name of the binary output file is the plan file name. So if it was the first plan, it might be P01, would be the extension if you go look on your hard drive. And when you run it, it'll make a file that has O01, or like a P05 will make an O05. A lot of things are done like that in our file system. And in that binary file, there will be some flags that tell you about some things that could have gone awry. And there's 3 categories, errors, warnings, and notes. Wherever they happen, for whatever profile, whatever cross-section, if there's a problem, it repeats. Or it tells you the message. And if the next one has the same problem, it repeats it. It doesn't say, hey, you have a lot of these problems. It tells you everywhere they occur. So what do we got here? We got the conveyance ratio, upstream conveyance divided by the downstream conveyance is less than 0.7 and greater than 1.4. So conveyance has to do with like the capacity for it to transfer water in that cross section. And at any given profile, we're saying that it dramatically was different. So why would it be dramatically different? Well, it either got way wider or way narrower, or the n value went way up or n value went way down. And let's see, so there's a bunch of conveyance ratio. Divided flow computed for this river, for this cross section. That just means that the top width is not continuous. Maybe there's a levee, maybe there's an island in the middle of the channel, and it's a warning, not an error. So maybe that's okay. You should just go look at that. This one here, it says may indicate the need for additional cross section. There's a couple others that are similar. If the water surface elevation changes more than a foot or something from section to section, then you get some warning like that. And then there's three similar kind of things that indicate you should probably have more cross sections. So why would you need more cross sections? Is that the equations we're solving, they're nonlinear. And the nonlinear part of it mostly is how we interpolate the energy grade line from cross section to cross section. And there's an averaging technique that we say we take the instantaneous one here, instantaneous one there. We might there's 4 different ways that we do that in different applications. But if you have good cross-section spacing, then the averaging technique doesn't really matter. We are solving nonlinear problems in a discretized manner, and you need to have cross-sections to characterize kind of what's happening. Those are the kind of messages you get. On the mean res window, there's a row of buttons, and one of them says, I think it's got that little picture right there. Little picture with colored notes, a little hand pointing at it, or it says error warnings and notes or something. Anyways, shows you that.
Like, how important is that warning about the conveyance ratio?
I would go interpolate cross sections in there. Can you ever go too far with that? I'm sure you can go too far with that. If the cross section spacing is like on par with how wide the river is, so like the channel. If the channel was 150 feet wide and your cross sections are about 150 feet wide, that's like a really good place to start with. On bigger rivers like the Mississippi, then they end up being closer than that because the Mississippi River is like miles wide. And you want cross sections maybe only a mile apart. Meanwhile, it's 3 miles wide. So that would be, the cross sections would be less than the width of the river. And you can get away with the cross section spacing being, anyway, that's the ratio I'd like to look at, is the width of the channel, a couple times bigger than that, a couple times smaller, or half fractions of that seem like a good way to do that. Other things to look at are just look at the profile. And if the profile is smooth and there's not anything interesting happening, then they can be really far apart. Where there's a break in grade or change or constriction or contraction or something like that, then there could be big dips or changes in the energy grade line. Then you're going to want to have more cross sections in those areas. Okay, and those are the areas that are going to give you messages like these. So it's a good measure. Like I said, maybe there are places where you can go too far, but it's a dramatic change. How else you see the error warnings and notes is that there's 2 basic tables. There's the node-specific table and then the profile table. On the node-specific table, which I think we came in here for the culvert one, we were in type culvert, and one of these messages down here said it was inlet or outlet control. So that's all of that table data, but down here on the bottom it also has those messages for this location for that profile. That other table we looked at was like all of them, but here's kind of a detailed, zoned in look at that. Okay, the categories. Errors, it'll keep the program from running. We try to not have too many of those. So if there really was something like if you didn't have the right data put in, then we'll stop you at the beginning. We talked about that error check at the beginning. Will stop you from getting there. Other problems, like you're doing subcritical analysis and you come to a point that's supercritical, the program we could just stop and say, hey, this is not the right way to compute this problem, but we don't. We say, well, okay, you asked for subcritical solution, but the real answer is probably supercritical. Well, we'll just default to critical depth for a while until it goes back to subcritical, which maybe never, but okay, so errors, not too many of those, and they really are what will make the program keep it from running. And the steady flow engine, I think I had some slides on there where I had it crash, and then years ago later I tried to make it crash again, and I couldn't find a way to do that. And in comparison to unsteady flow, you just make the time step really big and it'll crash right away. But the steady flow engine, even if you have terrible cross sections and they're spaced really far apart, it might give you terrible answers, but it does usually run. Which is, we'll call that a good thing. Okay, so there's errors. Warnings, just let you know. Notes provide information about the program and how it's performing. The one like the divided flow, I think we called that one a note, and it moved up to warning at some point where there was an island. Anyway, so there's 3 different flavors of them. But notes are just information about what happened, and warnings are things you should go look into that. Okay, so when it does crash, it will usually crash in one of two places. There's the reading in the data, getting going, and then the during computations. And it'll try to tell you down over here in some message, like what it was doing when it crashed. The only general guidance I have for you is it'll tell you a place, and if it tells you a cross-section, that, hey, I crashed trying to read this cross-section. Well, it actually probably didn't crash trying to read that cross-section. Most of the time, there's a bridge either just upstream or just downstream of that cross-section, because cross-sections are pretty solid. There's not many instances where just reading in a cross-section will make the program crash. It's usually out of structure. So when it crashes reading in and it tells you a location, go look in that location. But if you don't find anything, go look a little bit above and a little below it too. And we haven't had problems like that for a long time, but they still could be there. That's just reading the data in. But then there's also during computations that can crash too. Like I said, the steady flow engine is pretty bulletproof, so it's hard even to make it do that anymore. But if it does, it'll tell you where it's at, and usually it'll be out of structure of some kind. It most likely will not be a cross section. And if it is dying at a cross section, look at the structure just above and below. Okay, then there's some other things, and you might or might not have noticed, that this is the bridge editor, and there's some other places in RAS like this where we color code some of the merging of your data. So when you put in a bridge deck, this has got a nice curved bridge deck here, and then maybe some block obstructions over there. You should have it so that the start of your data is like down on the ground, and then it goes up, and then ends in the ground. So if your bridge deck, if your cross section looks something like this, and you wanted to put in a bridge deck that looks like this, start your data somewhere down on the ground. And if you start off with it comfortably down on the ground, then we will find this intersection, and that one, and that'll be great. You could try to be clever and say, well, I want to start right here, and then I want to follow the ground down to here, and then go up and down, and then follow it along, and so on. And if you do that exactly right, then that works out fine. But if you don't, you could end up with some extra holes in there that you did not intend. And I've seen that quite a few times, actually. Okay, so what is this graph? This graph has got some clues for that. And it shows you a red line. So the red line is going to be like, if there's weir flow, this is where it's going to be. I mean, this is what the program is going to consider weir flow. All the stuff above the red line. So here we got a red line right there, and over here, and so on. And this also is kind of, okay, so that's the weir line. Then there's the green line, and says, oh, this is what I recognized as the lid, and this is what I recognize as the ground for under a bridge. And if this one's like, well, there's green around the bridge there. What I wouldn't want to find is like see some green and blue down over in there. Here's a zoomed in view of that where the ground line was found here, and blue there, green there, all looking good. Then there's another option. If you go under options, there's another thing you can turn on and says, show me what you think the piers are. And if you turn that on, then it'll highlight the piers. So this one doesn't have abutments or sloping abutments. That's one that is that tool. But you put in a lot of data, and it's all kind of overlapping in this mess here. That I've got a sloping abutment that looks. We have a sloping abutment that goes like that. And again, start out in the dirt and have it finish somewhere in the dirt, so that when the blue line for the lid should go from here over to there, and then the green line should go along that, right? Because that was the purpose of adding that abutment, is you're trying to fill in that little area or something like that. So you add all these different elements, all of these different things up here. Take a look at it. Make sure the red line is showing where, if there's weir flow, that's where the weir flow's at, and if it followed all the other things you added in the middle to give us the opening that we wanted. And there's other places in the program with color-coded stuff like that too. Okay, log output. So by default, it writes a text file in the same where your output's at. By default, it writes out a very minimal amount of information to it, so it won't be a big file. And you can go look at that, and we'll see what it looks like here in a sec. There is a way you can change a logging level and a number from 1 to 10. And if you bump that up, then you get more and more output. And if you jack it up all the way to 10, then like when it does iterations on the structure or something, then it shows you all that. So the file can get pretty big. Anyway, so that is something you can do, and it's more like just figuring out how the program works. Not normally I'd go about looking at results from a run. Okay, so what do we normally do? Well, I like to start off with getting the big picture in the easiest way possible, and I find that is looking at the cross-section plot and looking at the profile plots. There is an XYZ perspective plot, so that's something there's an old one of those, and the new one is more like a game view. There's the old one from way back when, and then there's a much more like game level kind of thing for XYZ perspective plot. Okay, so I guess we might add, what we really should add right here is look at it in a RAS mapper too. You know, we spent a ton of time and effort on that. I mean, it does a really good job, shows you depths and directions, and you can turn on velocities and things like that. So look at graphics. So cross-section plot, profile plot, and then RAS mapper stuff. Okay, then, so those are the graphics. Those are easy and fast, and I encourage you to do that first. Then you can start looking at tabular data, and there's that node-specific one and profile one, and we'll look at those here. And I'm going to look at the cross-section plot, and I'm kind of scrolling through them. You can go put your mouse, or you go put your cursor up in there, and then once you've got that active, you can just wheel through them all, and or all of them in this river reach relatively quickly. And the kind of things I'm asking or looking at are like this question here. Like, really? If there's something that is 20 feet tall, vertical. I've seen stuff like that before. Is it a building, or what is it? And now that we've got Google Maps, it's relatively easy to go look, right? If you go over to RAS Mapper, turn on the web imagery, and look, just what are we looking at here? Other things we're looking at are when the water surface elevation is now below these ineffective flows, so it's saying that there is water out over there, but it's not actively conveying. And this is where, like around bridges, we want to make sure they kind of get triggered. That if the upstream part of the bridge says water's going over the bridge, then the downstream side should also say water's going over the bridge. And this is a good plot to verify all that is happening. Other things that I get out of this is I'm looking at the energy grade line, and it's on the order of a foot or something. Okay, that's fine. Inches, feet, fine. 20 feet, maybe not fine. So that would be an indication that water's really going faster there. So I always leave on the energy grade line. Encourage you to do so too. Okay, so that's great. That's the cross-section plot. So now we can go to the profile plot. And in this case, it looks like someone turned on that they want, that's critical depth, and they wanted it to be computed everywhere. Normally you don't have that on. It's kind of an expensive thing to compute, so we don't do it by default. But you can. It's under one of the options under the steady flow computation window. And what would I be looking for here with respect to critical depth is did the energy grade line, or did the water surface actually go to critical depth? And if it did, I'd want to know that. And if it did go to critical depth, is that a problem? Well, it depends. If there was like a break in grade, so there was a weir or something, then that's a fine solution. If it's just in the middle of somewhere, well, I'm not sure, because it could be steep enough to go through critical depth, but I would just want to know and think about that. Other things you can turn on the profile plot is you can turn on, if there's levees, you can turn them on, you can see them here. That way you can see that, hey, we're way above all the levees. There's a left and right levee, and the water surface elevation is above it on both sides. So a lot of information you can get out of the profile plot. Okay, so here's that same bridge editor. So the red line is the weir, green is the lid, and blue is the ground. And under options, like I said, there's another one where you can see, you can highlight the piers. And this one's pretty straightforward and looks just exactly like we would hope. Again, what we don't want is there to be, someone tried to put in the deck and they left a little opening right out over there. That's the kind of thing you don't want to have happen. This is an input table, and I saw Stan talked about this earlier. It shows you all the n values in the system, and what are the kind of things that jump out when you look at it? Well, there's the color aspect of it. Is the default is to show all regions, but you could say, I only want to look at the channel. And not only is it that I don't want to look at the channel, because maybe actually I want to do calibration, so I want to take all the channel values and multiply them times the number. Well, right now they're not even all lined up. So like here's the channel. This one must have just left channel right, so only 3. Where in this one's got 2 n values in the leftover bank, 1 in the channel and 1 in the right, and so on. This one right here has got 2 in the left, 1 in the channel, and 3 in the right. Okay, but if you just want to do kind of strategic multiplies of the channel ones versus the overbank ones, you could turn on just the overbanks, or you could do just the channel. Like if the procedure for calibration, a good procedure is to start off with just try to calibrate the stuff in the channel first. Because if you don't get the channel right, it's really hard to get the later ones right. So just start off with getting the channel calibration. So you're using one of your lower flow events or lower flow profiles, and then turn this category on to just channel, and then go do some blanket the whole thing, raise them up, or just strategic part of the table, raise them up in net fractions. But that's all good for input. But for output, it's also good to go and just have a look to see like what are the n values. So n value 0.25, that's really high. Oh, so if someone was trying to achieve something there, what were they trying to achieve? They wanted there to be no flow for part of a low cross section, right? No, they wanted to take the conveyance and say, well, way less conveyance is happening for whatever station this is. And then 0.15, that's really high too. So they're really trying to kill the conveyance for different parts of that cross section. And it looks like there's a bridge right here below. So what they're probably trying to do is trying to achieve something like what we normally do with ineffectives. So there still would be water there, still would be moving, but it'll be moving really slow because of those really high n values. Okay, so then the other good place to go is the mapping window. And when it comes in, you got your default depth, velocity, and water surface elevation that are done in dynamic mode, so it's not even putting a big file on your hard drive, but you get a lot of good visual information about what's happening in the model. So here's, we got our cross sections turned on, and we're showing a depth map. What are we showing here? So that it looks like the edge of the cross section didn't go to the edge of the levee. And in this case, it's showing a little bit of water on the other side of the levee. So what do we do about that? Well, there's a couple things we can do about it. One, we could go in and move the edge line, the mapping edge line, to line up with the top of the levee. That's probably the best solution. In this case, we'd want to move this edge out over there, because the program during the simulation is it will make a zone, it'll be the bounds of where water can go from cross section to cross section. And over here, it's even more dramatic, that your cross section line went from there to there, and then it makes a tin to cover that area, which will then be used to fill in this with water surface. And I didn't know about the terrain over here, so I just made a line that followed something like that. Well, that's not a very good line, because if it got wet over here, it probably got wet right there too, right? This is the levee. So this line should have been out over there. So when you run it, or in your RAS mapper, you could say complete the interpolation surfaces, and you'll see these lines over here, and you can edit them and move them out over to the top of the levee, and then you'll get a better inundation map. And there's another option, which I'll get on the computer here in just a minute, and we'll look at this situation right here, that we have an option on all of the maps, or at least on the depth and water surface map. And remember we talked about plot options? So you could turn on the properties window, and you could change the colors and things like that. Over on the right, there was other additional plot options. And one of them is called something like model boundary deficiency or something like that. And the thing we're getting at right there is the water being held up by an arbitrary line in your model, or is it being held up by the ground that exists real in the world? And because you can end up, if you have a big model, you might actually not see that. And realize that our domain actually is what limited the water, not the hydraulics, our domain selection. So I'm just saying that look for that, and that there's other tools that help you see that. Okay, so critical depth. 4 bullets there. So bad cross-section data. Up to your imagination to how bad it can be, but when it goes to critical depth, go look at the location, see if that's true, see what's up with that. Probably the most common one is here, the cross-sections are too far apart. So it was trying to balance the energy grade line, couldn't do that, defaulted to critical depth and kept going. Wrong flow regime. So this is that I didn't have good geometry. This is where I didn't run it right. I said run it subcritical, and it wasn't true. It was mixed flow. The mixed flow run actually works really well. Why do we not just make that always work that way? Well, it requires a boundary condition on the upstream side, and we didn't want you to make you put that in if it normally doesn't happen. Okay, then this last one is more tricky. It couldn't balance the energy equation above or below the top of a levee or ineffective flow region. So when you have a cross section, and you're limiting the flow by ineffectives or something like that, or levies. I guess those are the basic two options here. So you would have, let's say we had a levee that was at that elevation. So you're proposing a levee right there. So it's not really in the terrain yet. And that at one iteration, or it's trying to balance the energy grade line from the cross section down below, and it tries this water surface, and it says, well, it doesn't match. The energy grade line I get here does not match the projected energy loss. So it says, well, I will try something ever so slightly higher, namely this one. And then this one is way too high because there's all this other area out there than here. A lot more conveyance is happening. So it can be hard to balance, and it might not even be immediately clear what the right answer is. You need to decide what is going to happen over here if that does actually get topped. Maybe is full flow the right thing? Full on, all the conveyance over here is actively conveying downstream. If it truly is going over there and there's an issue about how much volume goes over there, does this thing fill up instantaneously? Well, probably not. So then you could model this, that we might end up being an unsteady model.
Unsteady flow?
Yeah, that's right.
Unsteady how,
Right,
how
because
much
if,
you want-
right, how much, it depends on, like, is this a really big hole or is it like a detention basin that actually people designed to take the top off of a hydrograph, right? That if an area is flooding downstream, what you can do is let the highest flows over to a stilling basin somewhere so that the peak flows don't make it down to the area of concern. And this is the kind of area where you start worrying about like the volume of the water going by, because in steady flow, we don't care about volumes. We say there's infinite volume. It's just happening. Whatever the flow is, it's that way for as much as needed to fill in everything. But and that's a decent approximation or there's a whole class of problems. That is a very good approximation too. But this one where you start worrying about what happens when it went over and filled in an area, then if this is a big area, then you start worrying about volumes. If it's a small area, you don't worry about it. And if it's unstable, you might go to ineffective flow instead of a levee. It's a source of potential problem. And what it's telling you is that the thing you're asking for is not really well suited to answer by the steady flow engine. And then you need to make a minor adjustment or something. You need to decide how you're going to deal with that.